So the next presentation is by Enrique on ground subsidence socioeconomic vulnerability in Salamanca in central Mexico. So please go ahead.
Thank you very much. Good afternoon. I just want to acknowledge that this is Katia's Villarnobo part of her dissertation. So I'm going to share with you some of her results. So just as a context, we recently finished a nationwide INSAR analysis where throughout the whole of Mexico, we analyzed around 1.8 million square kilometers, and we detected over 1,500 urban localities covering like almost 6,000 square kilometers, and where almost 29 million people live who are exposed to subsidence faster than minus 2.5 centimeters per year. So basically, the threshold that we set up was a little bit high. And if you haven't seen the details, I may suggest that you, before Enrique takes down the poster, you may want to go and take a look at the details of this survey. So the fastest detected subsidence that we detected, it was in eastern on the eastern side of the metropolitan Mexico City, with 24.8 centimeters per year. And setting aside that big urban area, the most vulnerable cities within the central Mexico industrial corridor are these three cities: Celaya, Salamanca, and Irapuato, which are over here. So you may ask yourself, having 1,500 places, where do we start analyzing and doing the brunt of the characterization and the analysis of these cities? And well, we decided this. We thought about doing these cities because of several things. One of them was that we wanted to do a test case or a pilot case and develop all the methodology that we might use later on for analyzing the remaining of all these cities. So just to put you in context, why this industrial corridor in the state of Guanajuato. It's Guanajuato, this province in Mexico City, is the 7th largest contributor to the national GDP. Manufacturing, agriculture, and food industry are its most important activities. If you live in the US and if you buy asparagus or berries or something like that, it's very, very likely that they will come from this area. Same thing, if you buy a car in the US, most likely it'll be built in this part of the country, or a large part of the components will come from this area. And this area, these three cities have a total population of a little bit over 1.5 million people. So our objectives in this, what I'm going to share with you today, are we want to reach three objectives. One is the general characterization of land subsidence in between 2014 and 2020. The 2020 date is because we wanted to align as much as possible with the data from the National Population and Economic Census. Then we wanted, the next part is we wanted to do to estimate the socioeconomic vulnerability of the people living in this area. And third, we wanted to do a socioeconomic risk to subsidence. And that's what I'm going to show you today. Further down the road and in the next months, we are in the process of doing an estimate of the associated economic loss in this part of Mexico. So just to set up the stage, Irapuato, Salamanca, Irapuato, Salamanca, and Celaya are cities that have been built or underlaid by alluvial quaternary deposits, and they are interstratified with tephra layers. Water supply comes from water wells from two major aquifers, the Irapuato Valle and Valle Celaya, which both show a decrease on their static water level of about 1.5 meters per year. So there's agriculture, and the urban expansion is taking a big toll on its aquifers. So the first part of the analysis, for the first part of the analysis, we use Sentinel data. We use two different orbits. We analyze this data set with ICE and the MinPy packages in order to get the INSAR time series. Then we did some custom coherence masking and mosaicing in order to get a seamless mosaic, and eventually use this cartographic product to create the hazard classification using the census data contained on the spatial basic statistical units published by INEGI, or National Institute in charge of those activities. So the first part is, since one of the objectives is to get as much, close to 100% retrievals from all the urban areas, and given the fact that usually you end up with these situations where different satellite tracks cover different parts of your study area, and usually this is what happens. You get your edge of different tracks within one of your targets. So what we had to do was to determine the best coherence level to maximize the urban areas coverage. And this is because we wanted to get as close to the 100% retrievals on the urban areas, because if we want to do counts on all sort of population and activities, we want to have all the data from all the cities. So that basically takes a little bit of tweaking, and also the masking and mosaicing in order to get a seamless composite is not that trivial. Basically, you need to do some custom work in order to create this mosaic. Once we create that mosaic, we can see that the subsidence footprint is developed over non-consolidated sedimentary deposits, and its subsidence process is driven by excessive groundwater extraction. This is just a small subset of water wells, but it's very well known to the water authorities that there's a fair number of water wells which are not declared, and therefore it's very hard to come out with a good water policy. So once we get our velocity maps, we can do two things. We can look at the agricultural land subsidence hazard, which you are looking at this based on the velocity maps, where we can do categories, and we can do a good aerial count. Here we found that the subsidence rates are up to 7 centimeters per year. That's just for the agricultural areas. But if we are looking at the urban areas, which is our main target this afternoon, this is what we get. We get a subsidence hazard map based on the INSAR velocity maps, where we can do our classification, and we can see that in the cities, the subsidence velocity is very close to the maximum on the urban areas. Here we get around 6 centimeters per year. Once we have that product, our next step is do a socioeconomic vulnerability on these areas. And for that, we use the 2020 population and housing census done by the federal government. And from that, we extract 13 parameters, which are a good, which are very useful to derive the socioeconomic vulnerabilities. And here's a list. Here's the list of the 13 of them, just to get you a sense of what they got. You get people with disabilities, population density per dwelling, whether the household is female, the literacy rate, whether the education level, access to internet, etc. So with these factors, we can normalize them, and then we can give them a weight in order to get a socioeconomic vulnerability using the hierarchical process defined by Sati in '87. So that product gives you this, that analysis gives you this kind of socioeconomic vulnerability maps, and that we can then derive or separate into different categories. And the next step is, once we have the subsidence hazard just for the urban areas, their socioeconomic vulnerability, then we can create a socioeconomic risk map by multiplying these products into a socioeconomic risk product. And this is what it looks like. And based on that, we can then do a very heavy analysis on the statistics for these areas. And for example, we can start looking at the percentage of the area subsiding within each one of the municipalities, or for example, the vulnerability, the subsidence exposed area per city or per municipality. And all this statistical and spatial information is very useful for, or we hope that it's going to be very useful for decision makers, for the different stakeholders, and to better prioritize the mitigation and or adaptation measures for both housing and critical urban infrastructure, and general public policy. So I'm going to show you I'm going to zoom in on all the three examples, or the three different cities, and show you the subsidence hazard, the socioeconomic vulnerability, and the final product, which is the risk to subsidence. And from this one, we can derive all the metrics that we can then use for this decision making. I'm not going to bother you with the details of the counts, but I'm just going to. This is Celaya. I'm sorry. This is Irapuato. This is Salamanca, and this is Celaya. And I'm going to show you some interesting things, because what you usually do when we do the velocity maps, you tend to think, well, if I were in the public administration and I were presented with this, you would say, well, let's see, our city rests over here. Downtown of the city is under a medium moderate subsidence, but on the edges we have all these very high velocities. So when we present this data to the policy and the local authorities, they usually say, well, let's do something over here in these areas. But if you take a closer look to the socioeconomic vulnerability and the final economic and the socioeconomic risks to subsidence, you can see that your target areas to work on these kind of mitigation or adaptation measures might not be the very first one that you think. So these are, we think, a very good startup to inform our decision makers about on one hand, the extent of the subsidence process in Mexico, which right now, if you ask them, they will say, no, nothing happens here. It's just a couple of cities. But now we can tell them, no, it's 1,500 cities and close to 30 million people, which, if you put it in perspective, that is 1 out of 5 persons living in the city, in the country. So it's a huge problem, and which hasn't been taken with the importance that we think it deserves. So just a few conclusions, and just to throw out just a few numbers so that you can put yourself in context, just for these cities. For the population that live in areas exposed to subsidence, it's over half of the people in Salamanca, almost half of the people living in Irapuato, and 85% of the people living in Celaya is exposed to subsidence. That is a big number. The municipalities with the largest affected subsidence are, again, these 3 municipalities, just in different order. And you can see that the maximum velocities are not trivial. And finally, we can tell you that the population exposed to a moderate and high socioeconomic risks to subsidence is close to 12% in Salamanca, 7% in Celaya, and close to 10% in Irapuato. And thank you very much.
Okay, thank you very much, Enrique. This is very convincing, I would say. So are there any questions? Yes.
Hello. Thank you for your good speech. I'm from Chinese, Shanghai Institute of Geology. I'm interested for your 13 parameters. I want to know, what do you think of your parameters of the students age between 6 to 14? That attended the schools. I want to you give me explain. Thank you.
Yes, these are the 13 parameters that in Mexico we have detected as the most important to determine the socioeconomic vulnerability. The population and economic census, they have like 250 different products from this one, derived from the census. But these are the ones that we find it more useful. However, the number that you see, have in mind that the number that you have here is the weight that we assign to each one of these products. So the first, you take the values out of these 13 parameters, then you normalize them, and then you multiply, you weigh them, and then you add them up as a total number to get the socioeconomic vulnerability. And that is what we use to derive the socioeconomic vulnerability. So these numbers are just the weight that we give them. But this is the list, and it goes with some houses still do not have concrete floors, whether the population is less than 14 years old, access to public service, the literacy rate of the family. For example, if the household is run by a female, or it's a complete family, if I shall say so, and things like that.
Okay. Any more questions?
Thank you for the presentation, for the nice presentation. I was wondering, you show a hazard map based on the velocity measurements. Do you consider also the time evolution of subsidence? Because this will change for sure the hazard grade of the different areas. Is it something that you're planning to do in the future?
Yes. Yes and no. And let me give you the full story. This process except for Mexico City, where we have known that this process has been going on for 130 years, in all these cities, this is a process that was triggered by the very fast urban expansion that happened in the 70s, where the country had a big boom, where there was infancy born, a lot of people, a lot of new babies, and a very fast expansion. And this detonated a strong growth of the cities. And that has been maintained in the last 20, 30 years, especially since NAFTA and all this economic boom in the country. This has been growing a lot, and that has fueled a big expanse of all these medium-sized cities. Now, from the experience that we have from the large analysis, basically, none of the detected subsidence areas have shown a decrease in velocity from the early 2000s analysis that we initially made. So, in other words, the subsidence rate has not, nor in these small, medium-sized cities, nor in Mexico that has a 100-year history, has in none of these cities we have seen a decrease on the velocity, except for one city, and that is a kind of an outlier. So yes, we know that the rates might change in the future, and this is something that we should be doing from time to time, but that the present rate, we think that given that we are taking very small, almost no measures to mitigate subsidence, the expectation is that there will be no, if any, there will be higher rates than the current ones. Yes. Yeah, but yes, I mean, this is something that you have to do on a regular basis. But on the other hand, this is the first wide nationwide area, and we think of it as the initial baseline from which we can gauge for the future.
Okay, I think it's enough for now at least. Okay, thank you very much for a very interesting presentation.